Hello students, we are going to see the few definitions, some more definitions in illumination. So in first class itself we have studied, we have know the difference between the illumination and light. Okay, light is the source, luminous plus, that is the source. From the lamp, electric lamp, the light is coming, that is the source. Illumination is when it is fall on the surface, how it is able to help to see the object, that is the illumination. You can define like this: luminous flux received by the surface per unit area. Okay, in a unit area, how the flux is received. Okay, so we can define by the symbol E, and then it is measured by the lux. Okay, or meter candle or foot candle. So we are going to see the next definition: lux or meter candle. Illuminations is measured by lux, which means the unit of the illumination is lux. We can define like this: illumination of the inside of sphere of radius 1 meter and a source of 1 cp is located at the center of sphere. If you imagine a sphere, one sphere is there. Inside that sphere has a radius of 1 meter. Okay, inside that, in center, okay, you fix the one source. Okay, if that source, when it is fixed in center, okay, if it is giving the 1 candle power, okay, that is the lux. Okay. Next definition: mean horizontal candle power. So based on the candle power, how it is distributed in all direction, in all plane, how it is we are reaching the candle power. So based upon that, we will have some more definitions. MHCP, mean horizontal candle power. It is defined as the mean of the candle power of source in all directions in horizontal plane. By the headline, by the heading itself, we can understand the definition. In a horizontal plane, in all direction, what is the mean of the candle power from the source? That is MHCP, mean horizontal candle power. Next one is mean spherical candle power. Means spherical candle power means actually MHCP, mean horizontal candle power, is only on horizontal plane. This one is in all planes. Okay, in all plans, we find out the mean of the candle power of the source in all direction. That is the MSC. M means spherical candle power. Next definition is mean hemispherical candle power. Mean hemispherical candle power is defined the mean of the candle power of the source in all directions above or below the horizontal plane. Here we see the 3 definitions. Mean horizontal candle power, means spherical candle power, mean hemispherical candle power. So first one is in all direction horizontal plane. Second one is all direction in all planes. Here in all direction above or below the horizontal plane. So next definition is reduction factor. Reduction factor is the ratio of mean spherical candle power to mean horizontal candle power. You take the ratio between MSCP and MHCP, which means the candle power in all plane, in all direction, divided by only in horizontal plane, mean candle power in horizontal plane. Okay, so reduction factor we can write like this: MSCP divided by MHCP. Next definition is lamp efficiency. We know efficiency Efficiency is the ratio of output power divided by input power. How much output you are getting for the given input, that is efficiency. If I give the more input but I'm not getting that much output, means the system or the thing is less efficient. Efficiency is less. So in electrical power we see the output power divided by input power. Same here, this is a ratio of total luminous flux emitting from the source to its electrical power input in watts. So illumination, what is the output? Output is the light source. Luminous flux is the output. What is the input? Input is we are giving the electrical power. That is the input. So the ratio between the luminous flux and the power input, electrical power input, is called the lamp efficiency. We can define like this: lamp efficiency equal to luminous flux divided by power input. So we will see one problem, so we can understand in a nice manner. This is the problem. At 200 volts, lamp takes a current of 1.2 ampere. It produces a total flux of 2860 lumens. Okay, so you just imagine one lamp is there, that is 200 volt. It is taking the current 1.2 ampere. How much flux, luminous flux it is giving? 2860 lumens. So what we have to find? We have to find out the efficiency. Here what is the data it is given? Voltage, current, then total flux, the luminous flux. What we have to find? Lamp efficiency. We know the formula. Lamp efficiency equal to luminous flux by power input. Okay, we will see we will solve this problem. So we know the power formula. Okay, V into I. So we know the voltage into current. So if you multiply these two, okay, we will get the power. Okay, so if you multiply 200 into 1.2, you will get like 12 into 2, 24. So we will get like what we will get? 200 into 1.2. We will get 24. 240, yes, and then if you divide by 260 divided by 240, you will get 11.91. So that is the lamp efficiency. So that is very less efficiency. Now we will see the specific consumption. We can define this specific consumption. We know consumption. Consumption means getting. Okay, for giving the output, what the energy is consumed, that is a consumption, right? The specific consumption we can define like this: the ratio of electric power input to its average candle power. For average candle power, how much electric power input is needed? Okay, there is a specific consumption. Next one is space to height ratio. Okay, space to height ratio. Okay, you can see the that head, that space to height. Okay, if there is a ratio between space and height, what is the space between what? We will see that. Horizontal distance between the adjacent lamps. We have two lamps. We mounted two lamps. Okay, there is a distance between the horizontal distance between the two adjacent lamps. If there is a measured distance, if we take a ratio between the distance and the height from the height of their mountings, okay, from the floor, okay, how much height it is there. If we measure the ratio, that is the space to height ratio, okay, horizontal distance, the ratio of horizontal distance between adjacent lamps to the height of the mountings. Next one is coefficient of utilization or utilization factor. What you have to do, this definition and all you have to write, and you have to try to understand one by one, because there is more similarity will be there. Our understanding is very important, otherwise we will confuse ourselves. Okay, utilization factor we can define like this. The source giving some light. In the working plan, some of the light is reaching, but how much light is useful, how much light is utilized for the work, you are getting? So that way we can define this. It is defined as the ratio of total number of lumens reaching the work plan to the total number of lumens emitting from the source. The ratio of luminous flux, working plan, in working plan how much light you are receiving, and then how much total number of lumens you are getting, emitted from the source. That is the utilization factor. Next one is maintenance factor. We can define the maintenance factor like the ratio of illumination under normal working condition to the after maintenance. If you clean the lamp, okay, if you clean the lamp, you will get the little more bright light, little more efficiency in a technical term. It will increase the efficiency, right? Here we can define the maintenance factor, the ratio between, in normal working condition, when it is not maintained, when it is not clean, that time how much light is there, and after cleaning, after the maintenance, after everything clean, how much illumination you are getting. So that is the maintenance factor. Here one note is given, its value is always less than 1, which means if you maintain, if you clean, it will be more, it will be less, of course. So automatically the ratio will be less than 1. If both are equal, you will get the value 1, but it won't be equal. If you clean the lamp, okay, you will get the more light, okay. Its value is always less than 1, it will be around 0.8. This is due to the accumulation of dust or dirt and the smoke. If anything there, automatically it will reduce the illumination, okay. So lamps emit less light than they emit, they are so clean. So frequent cleaning of the lamp will improve the illuminance factor. Okay, next we will see the depreciation factor. This is the reverse, okay, reverse to the maintenance factor. This is the ratio between initial illumination and then maintained illumination. Okay, it will be always more than 1. And then waste light factor. Waste light factor means if you use more than one source, okay, the light waves will be overlapped. but you can't use all the source fully. Means the extra light, that is a waste light factor. When a surface is illuminated by several numbers of the sources of light, there is a certain amount of wastage due to overlapping of light waves. The wastage of light is taken into account depending upon the type of area to be illuminated. This wastage is depends upon the factor which area it is illuminated. If it is a proper area, proper plan, it will illuminate it fully. Okay, there won't be any waste. So here the two things given. For a rectangular area, the light factor, waste light factor is 1.2. For irregular area, 1.5. Okay, for statues or monuments, the waste light factor is 1. The next thing is absorption factor. Normally, smoke or fumes, if it is in the atmosphere, it is there, it will absorb the light from the source. How much light is coming? Some of the light is absorbed. After absorption only you will get the remaining light. That is absorption factor. We can define like this: absorption factor equal to total lumens available after absorption divided by the total lumen out from the given lamp. How much illumination you are getting, how much total lumens you are getting, and then how much you are getting after the absorption. This is absorption factor. Next, this is the reflection factor. When light rays impinge on a surface, it's reflected from the surface at an angle of incidence. A portion of incident light is absorbed by the surface. Actually, if light is impinged on a surface and it is reflected, okay, some light is absorbed. We can define like this: the ratio of luminous flux leaving the surface to the luminous flux leaving the surface to the luminous flux incident, and it's known as reflection factor. Okay, so that is the reflection factor. Next one is glare. Okay, before I'm going to explain the glare, I will draw the diagram to understand the reflection factor. Here, one light is coming. This we can say incident ray, and then after that it is reflected. So here, if you draw the normal, you will get angle. So here, how much it is coming, that much will not be reflected. Okay, the ratio between the reflected ray and the incident ray, okay, that is called reflection factor. Next, we will see the glare. In our day-to-day life, we are experiencing the glare. Okay, light is important. Light we need to for seeing the object. Okay, visualizing the things. But if it is extreme level, the bright, very bright source, it will not be useful. It will irritate. Sometimes we are experiencing while driving, the vehicle is coming in opposite. The headlight is more bright. You can't see the object which is in opposite. Okay, that is a glare. The size of opening of the pupil in the human eye is controlled by its iris. The eye is exposed to a very bright source of light. The iris automatically contracts in order to reduce the amount of light and prevent the damage of retina. For damage prevention, the iris will close automatically. Then we can't see properly, even though there is a light. So that is imperfectly seen. In other words, we can say the brightness within the field of vision, such a character as to cause annoyance, discomfort, interference with the vision or eye fatigue. Okay, that is the glare. I hope you understood all the definitions. Now we will see the summary. In this lecture we saw the light, and then what is the science behind that, how the light is coming, and then definitions. Okay, and then we saw the definitions for saving energy and understanding the factors, maintenance factor, glare, wastage factor, glare efficiency. These are very important. And then we saw the illumination. Illumination is luminous flux per area, unit is lux. And then luminous intensity, that unit is candela, mHCP, mSCP, mHSCP. These ratios all we have seen. So up to now we have covered the definitions. We need to see the sources and the remaining basic things. These are the references: utilization of electric power and electric torque. J.B. Gupta, author is J.B. Gupta. And then art and science of utilization of electrical energy, author is Harpata. Thank you.